Welcome all. Now we are going to discuss the sixth chapter, continuity of linear maps, and the first theorem is theorem 6.1. Let x and y be normed spaces. If x is finite dimensional, then every linear map from x to y is continuous. Okay, and then conversely, if x is infinite dimensional and y is not equal to set 0, then there is a discontinuous linear map from x to y. Okay, so the important matter here we have to note is, if the domain of the linear map is finite dimensional, then the linear map becomes continuous. Okay, now we have to prove the first part. For that, suppose f from x to y is a linear map and capital X is finite dimensional. We know that when a space is finite dimensional, then it has a basis, right? Okay, if considering the case if x is equal to set 0, then we know that the dimension is 0 and we have nothing to prove here. Since if the domain contains only one point, it becomes always continuous, and so if x equal to 0, the result is clear. And if x is not equal to set to 0, then we can select a basis for capital X. Let it be a1, a2, etc. an be a basis. Okay, now we have to show that capital F is continuous. For that, we are selecting a sequence. Choose a sequence xn in capital X such that xn converges to x in capital X. Okay, so for showing capital F is continuous, then it is enough to show that capital F of xn converges to capital F of x. Okay, each xn is an element of capital X, right? So each xn can be written as a linear combination of this basis elements a1, a2, etc. an, like kn1 a1 plus kn2 a2 plus etc. plus kn okay, let the basis a1, a2, etc. am. Okay, then knm am. Okay, and since this is true for every n, and x element of x means that x is also a linear combination of a1, a2, etc. am, k1 a1 plus k2 a2 plus etc. plus kn am, like. Then we have chosen the sequence in such a way that xn converges to x in x, means that the corresponding coefficients converges. That is, the coefficients k and j converges to kj for every j equal to 1 to etc. m as n tends to infinity, since by the theorem 5.4b. Okay, then what about capital F of xn? We are going to check the convergence of capital F of xn. This is equal to capital F of kn1 a1 plus kn2 a2 plus etc. plus knm am, and this is equal to kn1 into capital F of a1 plus kn2 into capital F of a2 plus etc. plus knm into capital F of am, since capital F is linear. Okay, and this converges to, we know that kn1 converges to kj, that means kn1 converges to k1 into f of a1 plus kn2 converges to k2 into f of a2 plus etc. plus knm converges to km f of am. Okay, and this is actually f of k1 a1 plus k2 a2 plus etc. plus km am by the linearity of capital F, and this is nothing but capital F of x. That is, we have proved that if xn converges to x in capital X, then capital F of xn converges to capital F of x as n tends to infinity. This means that the function capital F is continuous. Thus, we have proved that every linear map capital F from a finite dimensional space X to Y is continuous, and that is the first part of the theorem. Okay, next we have to prove that if the space is infinite dimensional, if the space capital X is infinite dimensional, then there is a discontinuous map. Okay, conversely, suppose capital X is infinite dimensional. Okay, capital X is infinite dimensional, so we can take an infinite linearly independent subset of capital X. Okay, let set a1, a2, etc. be an infinite linearly independent subset of capital X. This is possible since capital X is infinite dimensional. Okay, now using this we are constructing some sequence like let xn equal to an divided by n into norm an. Okay, for n equal to 1, 2, 3, etc. Then capital L be the set of all these xn, that is x1, x2, x3, etc. is become an infinite linearly independent subset of capital X, right? And there is one more property, and norm of each xn is norm of an by n into norm an. This is 1 by n into norm an divided by norm an equal to 1 by n for every n. Okay, and we know that every normed space has a basis. So here capital L is an infinite linearly independent subset of X. So we can extend capital L to a basis capital B of capital X. This is from theorem 2.2b. Okay, also we have studied this in your linear algebra classes, that every linear independent set can be enlarged to a basis for the space. Okay, that is L is a subset of B, right, since capital X is infinite dimensional. Okay, now given y is not equal to set 0, okay, then we can choose a non-zero element from capital Y, choose B element of Y such that B is not equal to 0. Okay, Now we are going to construct the given the discontinuous function capital F. Define capital F from x to y such that f of x equal to this element B when x element of L, okay, equal to 0 when x element of B but not x element of L, okay. The rest part, when it is belongs to L, then the image is B. When it is belong to B but not L, the image is 0, and extend linearly for all other x element of x, okay. So we have defined capital F for the elements in capital L and the elements in capital B minus L, and then linearly extended this capital F for all other x element of x, okay. Therefore capital F is a linear map from x to y, and we have to show that this is the one we are going to mention that discontinuous function, right? For that, consider the elements of capital L, okay. We have sequence xn with norm of xn. We have already showed that norm of xn is equal to 1 by n. This is converges to 0 as n tends to infinity. That is, sequence xn converges to 0 as n tends to infinity. But when we check about capital F of xn, we get we know that xn is an element of capital L, so f of xn is equal to b for every n. This is not converges to 0 since b is not equal to 0, right? Okay, that is f of xn does not converges to 0. This is equal to capital F of 0, since we know that every linear map maps 0 to 0, okay. That is, f of xn does not converges to capital F of 0. Even xn converges to 0. We have already shown that xn converges to 0, but f of xn does not converges to f of 0. This means that capital F is discontinuous. Capital F is discontinuous map from the infinite dimensional space X to Y. So there exists a discontinuous map from every infinite dimensional node spaces, right? This is the proof.